This video explores the improvements to the simple saturation refrigeration cycle. In refrigeration, the basic reversed Rankine cycle provides a framework for understanding the thermodynamic principles involved in refrigeration processes. This cycle includes four key processes: isentropic compression, constant pressure heat rejection, isenthalpic expansion, and constant pressure heat absorption. Notably, it assumes that the refrigerant enters the compressor as a saturated vapor and exits the condenser as a saturated liquid. You can watch the video Introduction to Refrigeration to gain a deeper understanding of the thermodynamics of the refrigeration process. The link is provided in the description. In this video, we'll examine the modifications made to the basic reversed Rankine cycle to enhance its performance. This basic reversed Rankine cycle is also known as the simple saturation cycle. In this video, we will examine the following: 1. The use of an accumulator or pre-cooler, 2. The use of a flash chamber, 3. Subcooling the liquid refrigerant by vapor refrigerant from the evaporator, and 4. Subcooling the liquid refrigerant by liquid refrigerant from the expansion valve. First, let's examine the use of an accumulator. A refrigerant accumulator is used in the suction line before the compressor to prevent liquid refrigerant from entering the compressor. It ensures that only vapor reaches the compressor, preventing liquid slugging, which can damage the compressor. The accumulator allows liquid refrigerant to settle at the bottom, while only vapor is drawn into the compressor. Some designs include a heat exchanger or an orifice to help vaporize any remaining liquid refrigerant. Now, let's explore the thermodynamic processes of a refrigeration cycle with an accumulator. First, the dry saturated vapor from the accumulator is isentropically compressed in the compressor. Then, it undergoes a constant pressure heat rejection process from points 2 to 3 in the condenser. Subsequently, liquid refrigerant expands from points 3 to 4 and flows into the accumulator, which also receives vapor from the evaporator. The accumulator separates refrigerant into vapor, point 1, and liquid, point 4 dash. Liquid refrigerant flows from the accumulator to the evaporator, while dry saturated vapor goes to the compressor. From point 4 dash to point 1 dash indicates the constant pressure heat absorption process in the evaporator. Let's see how to determine the coefficient of performance in this improved refrigeration cycle. To do this, we must first establish the relationship between mass flow rates. Let M1 equals mass of liquid refrigerant circulating through the evaporator, and M2 equals mass of refrigerant circulating through the condenser. Considering the energy balance of the accumulator, we can write M2H4 plus M1H1 dash equals M2H1 plus M1HF4 dash. Here, we use the subscript F to indicate the liquid state at point 4. Rearranging the terms, we can obtain an expression for M1 in terms of enthalpy values and M2 as shown. Note that H4 is equal to HF3. The refrigerating effect, RE, equals M1 times H1 dash minus H4 dash. Substituting for M1 in terms of M2, we can simplify the equation as RE equals M2 times H1 minus HF3. This equation proves that the refrigerating effect is the same as that of a simple saturation cycle. The compressor work, WC, is given by M2 times H2 minus H1. The coefficient of performance, COP, is then given by the refrigerating effect divided by compressor work. This is equal to M2 times H1 minus HF3, divided by M2 times H2 minus H1. This simplifies to H1 minus HF3, divided by H2 minus H1. Using an accumulator in refrigeration systems does not alter the refrigerating effect, coefficient of performance, or compressor work, power, compared to a simple saturation cycle. Its sole purpose is to safeguard the compressor by preventing liquid refrigerant entry, ensuring only dry saturated vapor enters. Now, we explore the refrigeration system with a flash chamber. A flash chamber is used to improve system efficiency by separating flash gas, low-quality vapor, from the liquid refrigerant before it enters the evaporators. This ensures that only high-quality liquid reaches the evaporators. As refrigerant expands from the high-pressure condenser, some portion of it flashes into vapor due to a sudden pressure drop. The flash chamber separates this from the remaining liquid. Then the liquid is sent to the evaporator for efficient cooling, and the vapor is directed to the compressor. Let's explore the thermodynamic processes of a simple refrigeration cycle combined with a flash chamber. First, the dry saturated vapor flowing from the evaporator and the flash chamber is isentropically compressed in the compressor. Then, the constant pressure condensation occurs from point 2 to point 3. The refrigerant at the condenser exit that is in the saturated liquid state is expanded from point 3 to point 4. In the flash chamber, the refrigerant separates into saturated liquid, point 4-, and saturated vapor, point 1. The liquid refrigerant from the flash chamber goes through the evaporator from point 4- to point 1. The dry saturated vapor goes into the compressor along with the dry vapor from the evaporator exit point. We will now determine the refrigerating effect, compressor work, and coefficient of performance by first establishing the relationship between mass flow rates. Let M1 equals mass of liquid refrigerant supplied to the evaporator, and M2 equals mass of refrigerant circulating through the condenser or leaving the expansion valve. Then, the mass of refrigerant flowing directly from the flash chamber to the compressor is M2 minus M1. Applying energy balance to the flash chamber, M2H4 equals M2 minus M1 times H1, plus M1 H4-. Then, M1 can be expressed as M2 times H1 minus H4, divided by H1 minus HF4-. Since H4 is the same as HF3, M1 equals M2 times H1 minus HF3, divided by H1 minus HF4-. Refrigerating effect, RE equals M1 times H1 minus HF4-. Substituting for M1 in terms of M2, we can derive an expression for the refrigerating effect as RE equals M2 times H1 minus HF3. The compressor work, WC, is M2 times H2 minus H1. The coefficient of performance, COP, is given by refrigerating effect divided by compressor work, which is equal to M2 times H1 minus HF3, divided by M2 times H2 minus H1. This simplifies to H1 minus HF3 divided by H2 minus H1. From the foregoing derivations, we observe that the refrigerating effect, compressor work, and coefficient of performance are the same as those of a simple saturation cycle. The only effect resulting from the use of a flash chamber is the reduction in the mass of refrigerant flowing through the evaporator, hence the reduction in the size of the evaporator. It also ensures that no wet vapor is entered to the compressor. Let's now examine a refrigeration cycle that incorporates subcooling of the liquid refrigerant with vapor from the evaporator. In this arrangement, the refrigerant, after passing through the evaporator, which is at a lower temperature than the condenser exit temperature, is used to cool the refrigerant exiting the condenser via a heat exchanger. Let's analyze the changes in the thermodynamic processes and the performance parameters as a result of this modification to the simple saturation cycle. In the pH diagram, the points 1, 2, 3, and 4 represent the simple saturation cycle. When a heat exchanger is introduced after the condenser that is fed with the refrigerant from the evaporator exit is heated into the superheated state from point 1 to 1-. Then the isentropic compression is represented by the process from point 1 to point 2. The condensation of the refrigerant to the saturated liquid state occurs from point 2 to point 3. The condenser exit is further cooled in the heat exchanger from point 3 to point 3. The line 3 to 4 represents the expansion process. Constant pressure heat absorption in the evaporator occurs from point 4 to point 1. The refrigerating effect Re is given by m times H1 minus H4 Note that the mass flow rate is constant throughout. The refrigerating effect is increased compared to that of simple saturation cycle due to subcooling. The compressor work, Wc equals m times H2 minus H1 Since H2 is higher than H1 the compressor work is increased compared to that of simple saturation cycle. Then, the coefficient of performance, COP, is Re divided by compressor work, which is equal to H1 minus H4 divided by H2 minus H1. The analysis indicates that subcooling the liquid refrigerant with vapor refrigerant reduces the coefficient of performance, COP, of the cycle. This occurs because the increase in compressor power outweighs the increase in refrigerating effect. Despite the theoretical loss in COP associated with this method of subcooling, many actual installations still implement this process. Finally, we explore subcooling liquid refrigerant using wet refrigerant extracted after the expansion valve. This arrangement cools the liquid refrigerant exiting the condenser below its saturation temperature. To achieve this, a fraction of the refrigerant after expansion passes through a heat exchanger, where it absorbs heat from the refrigerant exiting the condenser. As a result, the liquid refrigerant is subcooled before entering the expansion device, while the extracted refrigerant is heated toward a saturated vapor state before being directed to the compressor. Let's explore the thermodynamic cycle and performance parameters when subcooling is achieved by using refrigerant extracted after the expansion valve. In the pressure enthalpy diagram, the simple saturation cycle is shown by 1, 2, 3, and 4. We now examine the processes when a heat exchanger is introduced to achieve the subcooling of the refrigerant after the condenser. The expanded wet vapor is superheated to saturation in the heat exchanger, and mixed with saturated vapor from the evaporator before entering the compressor, which performs isentropic compression from points 1 to 2. The condensation occurs from the point 2 to the saturated liquid point 3. The liquid refrigerant is then subcooled to point 3 flowing through the heat exchanger. The line point 3 to point 4 in the diagram represents the constant enthalpy expansion process. Line 4 to 1 in the diagram represents the constant pressure heat absorption process in the evaporator. We need to establish the relation between mass flow rates before calculating the refrigerating effect, compressor power, and the coefficient of performance. Let m1 is the mass flow rate through the evaporator, m2 is the mass flow rate through the condenser, and m3 is the mass flow rate extracted after the expansion valve. Considering mass balance, m2 equals m1 plus m3. Now consider the energy balance of the heat exchanger. M2 times HF3 minus HF3 equals to M3 times H1 minus H4. This simplifies to M3 equals M2 times HF3 minus HF3 divided by H1 minus HF4. Since HF4 is equal to HF3, M3 equals M2 times HF3 minus HF3 divided by H1 minus HF3. The refrigerating effect, Re, equals M1 times H1 minus H4. Since M1 is equal to M2 minus M3, substituting for M1, the RE is written as M2 minus M3 times H1 minus H4 dash. Further, we can write M3 in terms of M2 as previously derived and then simplify the equation for RE. The refrigerating effect is then M2 times H1 minus HF3. This is identical to the refrigerating effect of the simple saturation cycle. Although extracting a portion of the refrigerant to subcool the condenser exit reduces initial cooling capacity, the resulting subcooling ultimately compensates for this loss. The compressor work, WC, is equal to M2 times H2 minus H1. This is the same as that of the simple saturation cycle. The coefficient of performance, COP, is calculated as H1 minus HF3, divided by H2 minus H1. The preceding analysis demonstrates that the refrigerating effect, compressor work, and coefficient of performance are consistent with those observed in a simple saturation cycle. As a result, the configuration involving subcooling, where the refrigerant is extracted from the expansion valve, offers no discernible advantage. In essence, this approach to subcooling is thermodynamically equivalent to the simple saturation cycle.